All right, let's go ahead and take some time to discuss our next topic in Unit 7. So previously we discussed the idea of the kinetic theory of matter, how everything's composed of tiny little particles that are moving, and then how these particles can be moving a little bit, vibrating back and forth, or moving a lot, and that will determine if it's a solid, liquid, or gas. And you can go from a solid to a liquid, liquid to a gas, gas to a liquid, gas to a solid, so on and so forth. You have all these different phase changes. And so what I want to focus in on is one of those phase changes where you're going from a liquid to a gas, and that's the idea of vaporization. So vaporization, you can modify a bunch of different ways by having different elevations, by having different kinds of gases and different kinds of liquids present. So we're going to spend some time talking about vaporization. So just a little bit of review from yesterday. We talked about the idea of pressure. So pressure is the force divided by area. And so remember, if you have little gas particles, those little gas particles are hitting the sides of the container. And as they hit the sides of the container, they exert a force. That force per particular area is known as pressure. So here's a bunch of different units for pressure. You have kilopascals. 101.325 is the same as 1 atm of pressure, which is 1 atmosphere, which is the same as 760 millimeters of mercury, which is the same as 760 torr, which is the same as 14.7 psi. So in essence, every square inch of something is exerting 14.7 pounds of pressure. And so going back to what we did yesterday, one of those questions on the worksheet was, why don't we feel it? And just basically because we are used to that pressure. And so our body is pushing out the same pressure that is being pushed down by the atmosphere on top of us. So if we're looking at like a beaker, I got a beaker full of a liquid. The air pressure on top of it, pushing down, pushing on the side, pushing everywhere, is 1 atm or 1 atmosphere of pressure, or 14.7 psi. So all those air particles are exerting that force everywhere, on the bottom, on the top, on the left, on the right, and so on and so forth of the beaker as well as the liquid. So that's just some background information at 1 atmosphere of pressure. That is typically at the Earth's surface. So at the Earth's surface, we have 1 atmosphere of pressure. Typically, it can kind of range from like 1.01 to 0.99. That's why you have high and low pressure systems in weather, but we have on average 1 atmosphere of pressure at the Earth's surface. As you go higher up in elevation, so if I was looking at the Earth's surface, I would have 1 atmosphere of pressure. As I go higher up in elevation, as I go up to the mountains, as I go up in an airplane, as I go up in my hot air balloon, you're going to have less air particles because there's less gravity as you go further away from the surface. Less air particles results in less air particles hitting each other, hitting the sides of a container, resulting in less force for the same area, so you're going to have less pressure. So as you go further away from the Earth's surface, less air particles, less pressure, less force. So you'll notice closer to it is going to be higher pressure, more density, so on and so forth. And you also notice that it is composed primarily of nitrogen and oxygen. But the nitrogen molecules, the oxygen molecules, the argon, all the different gases, all those things added up together will result in 1 atmosphere of pressure. So if I have 78% of my atmosphere is nitrogen gas, 21% of my atmosphere is oxygen gas, 0.9% of my atmosphere is argon, and I had 1 atm of pressure, you can kind of look at it and go, oh, what is 78% of 1 atm? 0.7 atm of pressure is exerted from the nitrogen. I have 0.21 atm of pressure is exerted from the nitrogen. 0.09 atm of pressure is exerted by the argon, and the rest is 0.01. So in essence, all the different parts, the different types of gases present, proportionally will exert the amount of pressure dependent upon the percentages of that gas that is present. So just a kind of background information. But let's continue on talking about vaporization. So what is vaporization? Well, vaporization is the combination of both boiling and evaporation. Evaporation happens at the surface. Boiling kind of starts wherever your heat source is. So evaporation can happen even before the boiling point. So if we're looking at water, we know the boiling point of water is 100 degrees Celsius. And so water can evaporate at a lower temperature. In essence, what's happening during evaporation is you have at the surface, and only at the surface, do you have liquid water becoming a little more energy and forming gaseous water. And so it's evaporating. When you have boiling occurring, it's the same kind of idea, the process of liquid to a gas. However, this can happen when you're getting to that 100 degrees mark where you're actual liquids down inside the liquid are starting to turn into a gas. And then those gas bubbles are kind of forming to the surface, and then they evaporate from the surface. So one thing, just to kind of write this down, is vapor pressure is less than atmospheric pressure. So vapor pressure is the pressure exerted or put off by the vapor. And so what is vapor? Vapor is the gas from what is normally the liquid. So in essence, I have my liquid water. Any of that liquid water that turns into gas, that is your vapor. So steam is going to be water vapor. So in this situation where I have evaporation occurring, water vapor is less than the atmospheric pressure. When I get to the point of actually boiling, vapor pressure, so the pressure exerted by the water vapor or steam, is equal to the atmospheric pressure. And so that's where bubbles can form and rise actually in the liquid itself. And so that may be confusing, but we're going to go ahead and watch a couple things to kind of help us in our understanding what that actually means. So when water becomes vapor, go take a look.
After you've kind of seen the results of what happens when you start studying intermolecular forces, and we start making a little bit more of a condensed phase, such as solids and liquids, you start getting all these unique properties of solids and liquids. Liquids have quite a few unique ones: viscosity, surface tension, and one of the more unique ones is vapor pressure. That's a very special case, and that's probably another thing completely. So let's just think about it. If you take water in a container and you allow it to start evaporating, the space above the surface of the water will start getting water molecules. That means it's a gas now, and gases impart pressures. So as that builds up, what's going to happen is these particles floating above the water can go back into the water unless they're whisked away. So if you put a lid on the container, all the particles are trapped, so the water starts going back into the water phase, or I should say the water vapor goes back in. As this happens, you finally reach a state at which the exiting evaporation rate equals the entering condensation rate, and you reach what we call equilibrium. So when those two rates equal, you establish a constant pressure inside your container. And that pressure is called the vapor pressure of that liquid. In the case of water, you would say it's the vapor pressure of water.
And so one of the things he just said is vapor pressure. So that vapor pressure is dependent upon the temperature. If I increase the temperature of the water, more of that water is going to become steam or water vapor. So more of that water is going to become water vapor. And so as you increase the temperature, more water vapor, more vapor pressure as a result of that increased temperature.
It's an example of what we call dynamic equilibrium, meaning when you look at the thing, you can't tell anything's happening, but in actuality, there are billions and billions of molecules leaving the surface of the water, and there's also billions and billions re-entering, and they are exactly the same rate. So there's no net change, but you have established what we call a vapor pressure. And that's hopefully a little bit more of a handle for you on what vapor pressure is. We have other things to tell you later about vapor pressure in other videos.
Awesome. Thank you, Paul. So that's the idea of what is vapor pressure. So he kind of just illustrated the idea of vapor pressure. But let's talk about how vapor pressure can change. So looking at this in water vapor pressure and boiling.
We know that boiling is strongly influenced by atmospheric pressure. Pulled down by gravity, the air above us creates pressure, and that makes it difficult for bubbles to form and boiling to take place. We can think of atmospheric pressure as the collisions of air molecules against the surface of the water. That's the pressure. The more collisions, the greater the pressure. But water molecules can create pressure when they leave the liquid. As these faster moving water molecules escape, they collide with the molecules of air. This creates pressure, and we call it vapor pressure. In a way, the water molecules are pushing or colliding against the air molecules. This reduces the amount of pressure felt by the water. Back to boiling. Textbooks often state that when the vapor pressure equals the atmospheric pressure, boiling takes place. This is called the boiling point. Think of it this way. Atmospheric pressure pushes down, and that makes it difficult for the water molecules to spread out and form a bubble. But when the vapor pressure increases, molecules from the liquid escape, and they push against the air molecules and effectively reduce some of the pressure. This makes it easier for the liquid molecules to spread out, form a gas, and to rise to the surface. That's boiling. We can make boiling happen by either increasing the vapor pressure or decreasing the atmospheric pressure.
So he said you can affect the boiling point by either increasing the vapor pressure by increasing temperature or decreasing the atmospheric pressure. So by taking away particles from on top of it. And so by doing that, you could put it into a vacuum as well as you could take it higher up in elevation.
Either way, once the vapor pressure and the atmospheric pressure are equal, we've reached the boiling point and boiling can begin. One last thing. Different substances have different vapor pressures, and therefore they have different boiling points. This has to do with how strongly the molecules are attracted to each other in the liquid. The more strongly they're attracted, the less the vapor pressure, and it's more difficult to boil. Therefore, the higher the boiling point.
Perfect. And what he just said was the stronger the attraction to each other, the more difficult it is to boil. And so water is attracted to each other in the sense that we'll talk about in the future with hydrogen bonds. So it's difficult for them to kind of get to that level. So you have to increase the temperature. So other things to kind of take a look at here, this is known as a vapor pressure diagram. And so in essence, how much vapor pressure is present, and this unit here is torr. So this is just another unit for pressure. 760 is atmospheric pressure, or your typical pressure. And so if you're looking, as you increase temperature of water, so this line is for water, as you increase the temperature of water, you're going to get more vapor pressure, so more vapor. So if I had water at, let's say at 40 degrees, so if water at 40 degrees Celsius, I would have about 70, 80, I'm just going to round, around 70 torr of pressure exerted from just the water vapor. If I was to increase the temperature all the way up to 100 degrees Celsius, you'll notice that this is when water boils. And so at this point, you'd have 760 torr of pressure, which is the same thing as 1 atmosphere of pressure. So in essence, when the water vapor, so this is vapor pressure, when the vapor pressure is equal to the atmospheric pressure, it boils. So if I'm looking at ethanol at 78 degrees, the vapor pressure from the ethanol is going to be equal to the atmospheric pressure. That means ethanol is going to boil at 78 degrees. Diethyl ether is going to boil at 35 degrees Celsius. So you have all these different temperatures and these different pressures, all related to the vapor pressure. So major trend here that you see is as you increase temperature, you're going to increase more of the energy from the liquid. More of that liquid's going to kind of vaporize and become a vapor, resulting in more vapor pressure because there's more particles there. So you'll notice on the worksheet for today, let me make sure that it is here. You have a bunch of different questions that kind of go through that, and then you have this vapor pressure for 4 different liquids. And so I'm going to answer a couple of these with you guys and let you guys just do it on your own after that. So this now is not looking at torr, it's actually looking at another unit, kPa. So 101.3 kPa is also known as 1 atm, which is also known as 760 torr, which is also known as 14.7 psi. So if you're looking at this, looking at the graph above, at what temperature would ethanol boil? And so I have to figure out which one is ethanol. This is the line for ethanol. Where does ethanol come across this line? In essence, the question is asking, where is the vapor pressure equal to the atmospheric pressure? And you'll say, oh, right about there. That looks like it is about 80 degrees. And so you'd say 80 degrees Celsius. And so kind of just other things to take a look at. You can kind of try to figure these out. I'm just going to give you a bunch of different ways to look at this. And you can use that for your help. So go ahead and take a look at that. Please let me know if you have any questions. And that is that.